Okay, let's talk about quadratic functions today. We already know a little bit about them, but we're going to dive a little deeper. So, what is a quadratic function? First, we need to start with figuring out what a polynomial function is. A polynomial function has the format like this, where these things with a's and the ends at the bottom, those are constants. And we have an x, and then it's raised to some sort of power in descending order. So we have a constant times x to some power, another constant times x to a power below it, dot, dot, dot. These things are all optional. You can have however many terms you want to be a polynomial function. We have constant times x squared, which is what we're familiar with, plus a constant times x, plus just a constant. So all of these functions over here, these f of x's, f of x equals ax plus b, f of x equals c, just one constant, f of x equals x squared, those are all polynomials. We know ax plus b, that one is linear. F of x equals c, that is a constant function. Again, it's a straight line, but it's horizontal. And we have f of x equals x squared, and that one is our quadratic, our most basic quadratic. So after that, we can talk about quadratics and how they relate to polynomials. A quadratic specifically, let's write that out, quadratic is a polynomial with its highest degree, its highest power being 2. So that means our biggest term is going to be an x squared. So it's easy to see in this f of x, I have x squared. And g of x, now it looks like I just have an x, but when I fully multiply that all out and simplify it, I will end up with an x squared. Then in h of x, it doesn't matter that my x squared is behind my 9, it's still my highest degree. With this k squared, again, it looks like just an x and an x, but since they are multiplied times each other, I know that when I FOIL that, I'll get x squared as my leading term. Okay, and we have this formula here, f of x equals ax squared plus b of x plus c, and we're very used to seeing that. So this is our preferred order of writing our terms of our quadratics. Start with the x squared term, then the x, then the c. So let's do a little quick sketch. We already know how to do this, especially since we practice with transformations. Our parent function that we talk about a lot is just y equals x squared. So we remember our critical points. We have a critical point with this parent function with no transformations at 0, 0. We have another one at 1, 1, and another one symmetrical at negative 1, 1. And our graph just looks something like this, a basic parabola opening upwards. Okay, now let's look at sketching these graphs with some transformations, some stretches and compressions. So here we go. I'm going to start actually with a t-chart. I could plot it thinking about what this will look like, but I'm going to start with a t-chart of my critical x values. So I'm going to plug in my x values over here and my y values over here. So I'm going to do negative 1, 0, and 1. When I plug in negative 1, I get 1/3 times negative 1 squared, which is 1/3 times positive 1, which is just 1/3. I have 0, and when I plug in 1/3 times 0 squared, I only get 0. When I plug in 1, 1/3 times 1 squared is just 1/3 again. So let me plot my original graph really quickly, that original x squared function with our values at 1, 1. Here it is. And now I'm going to go ahead and plot my new graph. So my new graph at 1 is at 1/3, 0, 0, and a -1. We're at 1/3 again. So we really have that vertical compression. It's a lot wider than our original x² graph. And let's do that again with our 2x² graph. So if 1/3 made us have a compression on our x² graph, then 2 should have a stretch on our x² graph. So again, I'm going to plug in my critical points, and then I'm going to plug in my y value. So again, if I plug in my original points, 1, 1, 1. Now I'm going to plug in my 2x². And so at these points, I'm still going to have a 0, 0, but at x equals 1, my height is going to be 2. At x equals -1, my height will also be 2. So I have that nice vertical stretch. It's getting thinner. Okay, now we're going to talk about how we write our general forms of these equations. So our general form of a quadratic equation is what we're used to seeing. F of x equals ax² plus b of x plus c. And we use that for things like quadratic formula. That's what it's pretty useful for. Now we're going to talk about standard form, which we also call vertex form. And this helps us easily identify how to graph our function based on its vertex. So that's going to look a little like this. F of x equals a times x minus h² plus k. And we have that h and x that we already know from like the formula of a circle, very similar idea here. So h comma k is going to be our vertex. How we get from general form to standard form is by completing the square. If you don't remember how to do this, go ahead and watch that completing the square video, because I will not explain it in depth. I will just do it. Okay, so I'm going to go from this general form to vertex form. I need to complete the square, and the first thing I'm going to do is factor out that a term, leave room for my squared numbers, and keep that last term out of there. I can tell that 4 divided by 2 is going to be 2. Squared will get me 4, so I also need to subtract 4. Okay, and now I'm going to go ahead and move that 4, -4 outside, but remember it is multiplied by that 2. It goes out there with my 7, -8. Okay, and now on this step, I want to go ahead and factor that. I know that that factors to x plus 2 squared. And then this 7 and -8 simplify to -1. So now I'm looking at this. This is my vertex form. I can compare it to our kind of template vertex form. And I can see that we have a -2 up there. So my x value of my vertex will be -2. Remember, this negative is built into the function. So when I see a +2, I need to think, okay, that's subtracting a negative. And then our k value is -1. So our vertex of this parabola is -2, -1. Okay, now we do have a shortcut. If you've ever watched the proof of completing a square, we find here that this is -b over 2a from our general form. So let's try that out. Our a was 2, our b was 8, and our c was 7. So I'm going to plug in -b, which is -8. over 2 times a, which was 2, and I get negative 8 over 4, which is indeed negative 2. And we also learn that the y value is just what happens when we plug in negative b over 2a, our x value, into our general formula. So let's try that also. So my general formula, I'm going to do this up here, is 2x squared plus 8x plus 7. And remember, my negative b over 2a was negative 2. So I'm just going to find what is that formula where instead of plugging in x, I'm plugging in 2, negative 2. Okay, let's simplify this. 2 times negative 2 squared is 4, plus 8 times 2 is negative 16, plus 7. I get 8 minus 16 plus 7. Let's combine these. 8 and 7 are 15. So I have 15 minus 16, and I get negative 1, which checks out. That is my y value of my vertex. So I could go ahead and make a graph, and I don't know too much about this parabola, but I do know that it has a vertex at negative 2, comma, negative 1. So here's my vertex. It's got a positive a value, so I know it's going to open upwards. It's got a vertical stretch of 2, so it's going to be a little skinnier than normal. So I can imagine it might look something like this. Okay, so now we're going to talk about, we already talked about vertex form, but we're going to talk about factored form, which is how we can identify our x-intercepts. So I'm just going to go ahead and walk through again, turning this function into its vertex form. But we're also going to do factored form too to compare. So again, I want to complete the square. I'm factoring out that negative 1. I'm leaving room for my squares here. And I'm leaving my negative 8 outside. I know that whatever goes here is going to be my middle term divided by 2, and then squared. So 6 divided by 2 will be 3 squared. I'll get 9, and then I need to subtract that 9. Okay. Now I'm going to simplify again. I'm going to take that negative 9 outside, but I need to remember it's being multiplied by that negative. So that becomes a positive 9 on the outside to combine there. I'm going to go ahead, I'm going to factor the inside terms, which would be this part, and I know that I'll get x minus 3, and I know it's minus because that middle term is negative, squared, and then I will combine these like terms, and I'll get plus 1. So this is my vertex form. I know that my vertex is going to be at the point 3, comma 1. And my parabola is going to face downward because my a value, my leading coefficient, is negative. Okay, and I know that this point here is at 3, comma 1 so far. Now, it's probably going to look a little like this, and I want to know, is there an easy way to find out what my x-intercepts are? Well, there is definitely an easy way to find that out from our general form. The only thing I'm going to do is I'm just going to factor. So I can go ahead and keep my negative outside again, and I have x squared minus 6x plus 8. Now, when I factor this, I'm going to think about the fact that I need x's as my first terms, and then I'm going to need probably 2 negative terms since my inside number, my middle number here, is negative, but my outside number is positive. Okay, and now I need to think of 2 numbers that multiply to 8, but add to negative 6. If you use another factoring method like the magic square or whatever, go ahead and do that. But I can already see that negative 4 and negative 2 multiply to 8, but add to negative 6. So this is already my factored form of the equation. These here, we already know how to set polynomials equal to 0 and find their roots. We set the y value equal to 0, right? Because at the x-axis where our x-intercepts are, the height is 0. Okay, so I can take both of those factors separately and set them equal to 0, and I get that my whole polynomial, my whole function equals 0 at x equals 4 and at x equals 2. So putting that all together, I know that I have x-intercepts at x equals 2 and x equals 4. I know that my vertex is at 1, 2, 3, 1. And so it's going to look something like this. Okay, so now we went from general form through standard form, vertex form, factored form, in order to find out a lot about the graph of this function, but we can also go backwards. We can go from having the information of vertex and a point or x-intercepts in order to write an equation. So they tell us that our parabola has a vertex at 1, 2. So that's my h value and that's my k value. So I'm just going to write what I know so far. My f of x equals, I don't know that a value, but I do know my h is 1 and my k is 2. Oops, don't forget that squared. It's quadratic after all. All right, so this leaves me a little bit confused because I don't know what that a value is. I've used up what they told me about my vertex, but I still have this point P that's on my graph. And if a point is on my graph, that means when I plug the x value and y value into my equation, that statement is true. So we can also call, this is an x value, my y value, we're going to call that my f of x value. Y is the same as f of x for a function. Okay, so what's going to happen is I'm just going to plug those 2 points into our standard form equation and solve for a. So I'm going to do that down here. Instead of f of x, I'm going to put -6, our f of x value. We've got a, because I don't know what that is yet. And then instead of x, I'm going to put 3 minus 1 squared plus 2. Now I'm just going to keep simplifying and solving for x. And I get that my a value is -2. So I can just go ahead and substitute -2 where it belongs. Okay, so now I have my full equation in standard form. If I wanted to, I could FOIL this out and simplify it and put it into general form, but we don't need to today. Okay, so now we're going to talk about problems that are called optimization problems. We're talking about optimizing whatever it is we're trying to achieve. So we talked about when we have our a value, our first term is positive, our parabolas open upwards. When our parabolas open upwards, we're going to have a minimum value at our vertex. So something that would be optimized when we have a minimum is like cost, right? We want to spend the least amount of money possible. So our situation is optimized when we have the lowest cost possible. Now, something that we would want to maximize is like profit. We want to make as much money as possible. And we know that we have a maximum at our vertex, right? It's the top point, it's the peak of that parabola. We have that when our a value, our first term, is negative. So let's read this problem. A real estate company's profits P depend on the number of weekly listings X and are described by the algebraic representation P of X equals -5x squared plus 100x plus 20. What is the maximum possible profit? And we can tell that we're going to have a maximum anyway from this equation because our first term is negative. So our parabola will look something like that. So now I know that I need to find the vertex. What happens on the x-axis is the number of weekly listings, number of listings. And what happens on my y-axis in this problem is our profit. So I can find my profit by finding the y value of that vertex, and I can find out how many weekly listings I need based on that x value of my vertex. So let's go ahead and let's do this the long way. Let's just complete the square for this equation. So I'm going to factor out -5, my leading coefficient from all those terms, and left with x squared minus 20x. And then I'm going to leave room for my square numbers I'm looking for to complete and keep that 20 on the outside. -20, so two -10s will add up to -20, and I square that -10 to get me 100. Now I want to move this -100 to the outside, but remember that's multiplied by 5. So let's just do a little bit of cleaning up. Okay, and this is what I'm left with. I'm going to factor that to x minus 10 squared, and then add that 520 together. So this is my equation in vertex form. And I can tell that my x coordinate of my vertex will be 10 and my y value will be 520. So I need 10 weekly listings to get me a $520 profit, and that is the maximum amount. Now we could do that every time. We could complete the square, or we could remember that our vertex is also our -b over 2a, and then our y value is just that x value plugged into the function. Okay, so let's test that out. Our a is -5, our b is 100, our c is 20. -b over 2a, that would be -100 over 2 times -5. I get -100 over -10. Let's simplify that to +10. Okay, that matches. Now I'm going to plug that into my function. So that would be -5 times 10 squared plus 100 times 10 plus 20. Simplify, we get -5 times 10 squared, which is 100. -500 plus 1,000 plus 20. So it would be -500 plus 1,020. And I simplify that to +520. Okay, so I can see that these are both two methods to get me the same answer. Okay, let's do one more optimization problem because this one is kind of confusing in how they're wording it. So we need to get comfortable with drawing some examples. So suppose you have 100 meters of fencing, 1,000 meters of fencing to buy 3 rectangular corrals. Okay, I'm going to draw the picture like so. They would give you a little bit more instructions, like the corrals all have to be the same length, things like that, in order for you to be able to draw a picture correctly. So I'm going to go and label these sides. Our rectangles will all have the same sides, and then they'll all have the same lengths too. So I can make an equation out of this, right? If the black stuff is all fencing and I can only have 100 or 1,000 meters of it, I know that 1, 2, 3, 4x plus 1, 2, 3, 4, 5, 6 y will need to add up to 1,000. I'm just going to simplify that because I can see I can divide by 2 everywhere. Oops, that's a y, 6y. Okay. And then it says, find the dimension so that the total area is as large as possible. Okay, now looking at this function, my constraint function, that's not a quadratic. I can't find a vertex of it. That's just a linear equation that looks like this. There's no limit. There's no maximum or minimum. It goes on forever. So I know somehow I'm going to need to get to a quadratic equation. So here's my constraint equation. That's what we're going to call it. But they're also asking me about area. I know that area is x times y. Okay, now I have multiplication. I can see that I'm getting somewhere that I might have a quadratic. But with a quadratic, I would need an x squared. What I can do is I can substitute y with y equals from the other equation. But that means I need to put this in y equals form first. So to do that, I'm going to subtract 2x from both sides. I get 3y equals negative 2x plus 500. We have to divide by 3. I get y equals negative 2x plus 500 over 3. Okay. So now I'm just going to substitute that amount up in here. So now I have area equals x times, and I'm going to plug in that negative 2x plus 500 over 3. It's going to happen. I get a equals, and then I'm just going to distribute that x, negative 2x squared, and that's over 3 plus 500 over 3x. Okay. Now I have a quadratic. I have a negative 2/3 as my a value, and I have a 500 as my b value. My c is just 0. Okay, instead of completing the square, that's just too much, I'm going to use that little shortcut of finding negative b over 2a, and then inserting that into my function. And when I'm talking about the function, I'm talking about this new quadratic function. So let's find negative b over 2a. Our b is 500 over 3, so that's going to be negative 500 over 3, all over 2 times a, which is negative 2 over 3. Okay, so I can simplify that to negative 500 over 3 divided by negative 4 over 3. Now remember I said, instead of dividing like a mega fraction, we don't like that. We're going to multiply by the reciprocal, which is upside down. So we're going to have these 3's cancel out. I get negative 500 over negative 4, which will simplify to positive 125. So our biggest x value, our biggest length, would be 125. I want to find, that's not what the question is asking me. It's asking me find the dimensions, right? So I can find this equation. When I do so, I will get y equals negative 2 times my 125 plus 500 over 3 simplifies to y equals negative 250 plus 500 over 3. Y equals 250 over 3. And I can leave it like that, or I can simplify that to a fraction. So my dimensions would be my x has to be 125 meters, and my y has to be 250 over 3 meters. And they're asking me also, what is the largest area I can have? I can plug this x back into my area function, my new area function. So if I want to do that, I'm going to use black for this. My area equals negative 2/3 125 squared plus 500 thirds times 125. I could go through and simplify that. So I can multiply that and get negative 2/3 times 15,625 plus 62,500 divided by 3. We'll keep going. Negative 2 times 15,625 will get me negative 31,250 over 3 plus 62,500. When I simplify that, I get positive 31,250 over 3, and that simplifies to around 10,416 meters squared would be my maximum area.